Hello guys, I'm Tu. In this video, I'll be talking about role forming simulation using NX10 software. So let's begin by showing the example files. So this is the files, sim files. Double click on it to open it. Okay, so this is the example I have about NX doing role forming simulation. So let's begin by talking about the meshing. So just proceed to the meshing, and so this is the 1D collectors, which contains the rigid beams element. This rigid beams element is to serve from the center of the each roller to the surface of the roller. So this is a way that we enforce the node at the center here. Thus, the dependent nodes will all move together. So this is how we enforce the rotating motion of the roller. Okay, now let's look at the dummy thick steel. So these are the dummy surface. So the properties are just steel material and the thickness of 0.001. So this is just to serve as a rigid surface to deform this part of interest. And this is a couple, this is a tube actually. So this mesh has a property of 1 mm thick couple. And the properties is, this is a mat 1, 2. The default thickness is as such. So let's look at the material definition. Mat 1, 2, edit the selected material. So it has a density as such. So I think this is something which is incorrect. So this should be kg per meter cube. So there must be some mistake when I translate the input file. The unit is not consistent, and therefore I'm getting this kind of value. But for your purpose, I hope you can change it to the more realistic value. For example, kg per meter cube. By doing so, probably this value will need to change as well. So for example, change it to a value which is more reasonable, such as this. Anyway, I'll just keep it that way because what I'm currently showing you is about role forming simulation. You need to define these three important parameters following with a stress strain related properties. So this is the stress strain H parameters. So what is this value? So to understand more, we can look at the help files. So I'll just press F1 to activate the online help. So from here, we'll search for material 1 and click OK. So we can look at material 1. So there is no H parameters. Probably we should look at material S1 because this is related to the stress strain property. So material S1, there is a H here in the fifth column. So the H refers to as such work hardening slope in the unit of stresses. So there are more details can be found in the advanced nonlinear Let me just show you. So in the NX Nastran documentation, from here we can study on, if we would like to know more, we can go ahead and study the information here. So material S1. Okay, so anyway, let's continue as such. The type of nonlinearities, TYPE. So again, we can look in here. The type of material nonlinearities, and the plastic and the yield function criteria, von Mises, hardening rules. All this can be found in here. So all this can be found in here. The yield Fy, the yield function, the hardening rules, the limits, and so on. Okay, so I'll just proceed. So that's it about the meshing and also the material definition. So let's look at the boundary condition. In NX10 we have this load set. So it's a new thing, new load set. We can define load set to actually define combinations of loading. So let's begin by creating a new solution. So by doing so, you can know how to do a new solution from scratch. So from here, choose the solution type to solution 601.129. So the solution 6 in general terms, solution 601.106 and solution 601.129, the difference is this solution 106 does not take into account the inertial effect, but this does. Solution 129 take into consideration of the inertial effect. So for this simulation, I'll just keep it this way to use the solution 129 as suggested from the example file. So just give it a simple name so that you can understand. For this simulation, let's begin from the tabs available here. In the general tab, we are not going to change anything. The file management, executive control, nothing to change. The case control, we will need to define a time interval, time step intervals. If the row forming simulation, the total duration is 2 seconds, then we will need to define a time step, total time duration of 2 seconds. So for example, if we click create time step intervals, there are several definitions already done. So for example, my times 1, if I double click on it, these are the values defined. So in this definition, 125 steps, each step contains just 0.008 seconds, and I would like to collect the results. Each 5 of the steps collect 1 result. So that means I will have, based on this definition, I will only have 1 to 5 divided by 5, 25 steps of results. Okay. And for time step number 2, my time 2, so this will have 1000 steps. Each step contains 0.001 second, and for each 10 steps, collecting 1 data. So I will need to put these steps into the solution 1, for example. So let's let's highlight the steps that I want to put and choose add. Again, choose add. So this is the sequence of the time. That means I will perform this first, following by this. If you change the sequence, then it will begins with time step number 2 instead of number 1. So this is something to be aware of, because if you mess up the time step, you might not getting your result correct. So which should be first? So let's look at my time step 1. This increment is relatively large, okay, 0.008, as compared to my time step 2. This is 8 times smaller, 0.001. So probably in the beginning, we would like to choose a coarser time. It's a larger time. So for this example, we will keep the larger time step in the beginning to apply the bending, and smaller time step is used to when the rolling motion begins. Because rolling motions is quite complicated, therefore we need a smaller time increment. Okay, so therefore 1 and following by 2, close. Strategy parameters is another important thing. So click on create a modeling object. For this kind of simulation, you will need to define the strategy parameters to help you to converge each of the time steps. So these are all the keywords that we will need to study and understand about it. So probably you might feel overwhelmed with all these parameters. So I'll just show you the parameters that are defined from the standard examples. For example, here, click edit, and if we click on the preview, we can look at the keywords, the keywords that are defined. So those keywords that are shown here are those user-defined keywords. User-defined keywords. If those keywords that are not user-defined, default, they are using the default values, then the parameters will not be shown. Okay, only the user-defined keywords will be shown. Those default values, default keywords, they are not shown here. So in this example, this is the ID of this strategy, following with the auto, representing the automatic time stepping. So auto, they change to ATS. And another important parameters, the keywords NS step for stabilizing the mesh. So NS step, stiffness metric stabilization is used for this example because there is no boundary condition defined on this pipe in the initial condition. There are only boundary condition defined at the roller to enforce the rolling machine and also the bending, the rolling motion and also the bending motion, but there is no boundary condition to constrain the pipe. Therefore, this will play an important role to stabilize the initial conditions, because this mesh is initially floating in middle of air. Okay, so this is to stabilize the mesh, to allow some damping so that this mesh will not fly away. So okay, that's it. Then line search is a algorithm within the calculation. So for more information, you may search for the line search. So from this here, you can try line search. So sometimes line search is useful to help on convergence, but sometimes it's not. But for this example, we'll just follow the recommended settings to allow line search. So these are the line search information. Next, max iteration. So the maximum iteration, the default value was 15, and it is now changed to 30 to allow a longer iterations step That means in each iteration, 30 steps is the maximum calculation value. So if in that particular iteration, the steps used to converge is more than 30, or in other words, if the graph of convergence does not converge within 30 steps, then the iteration will stop, and following with the other strategies. For example, following with the automatic stepping strategies to reduce the time stepping and continue to reiterate again. Okay, so these are some of the important keywords that is required for this simulation. Okay, so if we are not sure what are the others means, what are the keywords, the other keywords means, for example this, we can always check in the Siemens help documentation so we can understand better. There is another way to study the strategy parameter as well. For example, if you see so many tabs for the strategy parameters, we can do a screen capture for each of the page. Then we can study one by one. For example, if I capture all the page, so we can study one by one the required what are the defaults and what are the user input. So for example, if I create a new strategy parameters, create a new one. So these are the defaults value. If I click on the preview button, you can see that all the attributes are at their default value. Therefore, there are nothing listed inside here. So we can see these are the default values, and we can compare with the values here to find out which are the user-defined value for that particular analysis. So I hope I made myself clear. You can use this method to study the parameters. Okay, the next thing we'll look at is bulk data. There are nothing to change about the simulation model. We are not going to change or add any nodes elements to the simulation model, thus nothing to do here. For the parameters, we need to enable last strain because this simulation involves strain more than 2%. So I believe this is the definition for last strain. Whenever your simulation involves strain more than 2%, then you will need to enable last strain. So that's it about the solution settings. We'll just click OK here. Now let's begin with the load set. So just right click here. We can create a new load set. For example, this is a transient event. So transient means this is a timely event. We'll be creating a transient excitation load set. And there are some types here. For example, for example, according to the example I have, they actually define a force load to but a very small insignificant load to the practical result, but this tiny load will help on the convergence instead, convergence of the solving. So apply loads is used. So we'll define an excitation. So this excitation is to define the timely manner of this load. So we create a new table to define the time. So for example, this is clamping motion. I just name it as a clamping motion. And you can see here, this is a time graph, dimensionless. So I believe this is the scale factor. So if you put just 1, that means we're trying to apply 100% of the load. So for the time, we can just try to always begin with 0, 0. So that means in time 0 seconds, the loading is 0. Then following with 1 second, and the load is 100%. And probably in 10 seconds, the load is also 1. So that means this load is applied from 0 second to 1 second, and after that the load is remain as 1. Okay, so that's the time manner, and we'll click OK. Now from here we'll create a new static load. The type already defined when we are choosing applied load. So apply loads, and from here again we'll choose force load. From here we'll choose so according to the example in here, you need to define this loading condition at 2 points. So I need to know the node ID in this case. So the way I find the node ID, I can read from the previous solve. So this is my previous solve input file, last run input file. I can just right click here and choose edit with notepad, or edit with a notepad, open with notepad. From here I can find the required data. For example, this is load set keyword. So I just need to find, for example, I found it. This is the force input. Force ID 116 acting on node 1401 and node 6081. And the magnitude is 50. Okay. So let me just apply this, and let me just choose on node 1401. So 1401 and 6085. Click OK. 6085. Click OK. And OK. So I'll be applying at group number 2, which contain these 2 nodes. You can see here they are highlighted. And the magnitude is 50 millinewton. So 50 millinewton is equivalent. 50 equivalent to 0.05 Newton, and is equivalent to 0.005 kg, which is 5 grams. So this is just 5 grams of magnitude, just to help on the convergence, I believe. So we just click, and also don't forget to check the direction of the force, which is in the y direction, so that this force will try to touch the pipe to the roller. Click OK to accept it. So this is the first definition for load set number 1. Now let's define another load set to press the roller together. So let's create a new load set, a transient excitation load set. And this time we'll be using enforced displacement instead of apply load. We'll be using enforced displacement to force the roller to come close together. By using the same excitations, we can use the same graph, the same view. Select existing table, the clamping motion, for example. OK. And click OK. Now let's create a new static load. And the type already predefined by us in the previous step. Click OK. And from here we choose new enforced motion load. And from here we choose unique value for each of the DOFs. Turn off the 1D mesh. Now let's click on the middle. This is node ID number 1, node ID 505, and also node ID 785. So there are 3 selected. Now let's look at edit per nodes. So what I'm trying to do now is to enforce the roller to come close together. Click here, and I'm moving in the Y direction. So here, Y direction referring to DOF number 2. So again, look back and at the input file, we can have some hints in the DOF number 2. This is the keyword for force and force displacement, SPCD. The ID for this force definition is 112, and the nodes are the nodes apply is 1, 505, 785. So which is according to here. Now the DOF and force are 2. So we are going to apply at DOF number 2. So these are the values to apply. So we can just put minus 1 E minus 6. Same goes for this. Okay, minus 1 E minus 6. 785. So this will be 0.035. So 0.035. So imagine this point is going up in the y-axis for 0.035. This will going up, and this will come down slightly. These two will come down slightly, so that this pipe will be clamped. So now let's click OK. So these are this definition is done. So we click OK. So currently we have two load set defined. Now let's proceed to define the load set for the rotating motion. So just right click here, create a new load set, transient excitation load set. This time is also an enforced displacement, but the time will be different. The rotating motion will begin after the clamping motion. So we need to define a new table. So from here, always begin with 0, 0. So in 1 second, the scale factor is also 0, because this is the moment of the clamping. We are not going to mess up the clamping. Then we can continue to define, let's say, at time 2 seconds, the scale factor is 1. So this is the clamping time, and this is the rotating time. Now click OK. So click OK. So now let's continue with a static load set and define enforced motion loads. From here, we are going to select these 3 nodes again, 1, 505, and also 785. So there are 3 of them. Unique DOF values for each of the nodes. So we click here, and this time we are going to change this we are going to enforce in the rotational x-axis. So this will be the DOF number 4. So from here we can read back. This is the definition. DOF number 4 for node ID number 1, minus 3 radian. So this is a unit in radian. So radian is not sorry, it's not shown here. Anyway, we'll just keep it as radian. So this is minus 3, and 3. So this is to say that from 0 second to 1 second, nothing is moving, no rotation motion is performed, but from 1 to 2, the rotation will perform for 3 radian. So I need to change this degree, change to radian. So this is radian. Okay. And okay. So then I'll just quickly double check whether my value is correct. So let's look at load. So 50 millinewton, this is my previous solution. It's already converged, so I'm just double checking my definition. So it's 3. Okay. The clamping motion is from 1, 10, 1, okay. And let's look at the rotating motion previous defined. Okay, yep, so 1, 0, 2, 1. Okay, so the definition is correct. So I have already defined all my load sets, and the next thing I'll be doing is constraining the rollers. So just from here, choose user-defined constraint, choose these 3 nodes again, fixing all the DOF except DOF number 2, because DOF number 2 is enforced, and DOF number 4 also free, because DOF number 4 is enforced by the load set, and click OK. So finally, we are going to define the load and the constraint are well defined, and we're going to define the context. So from here, we're going to click surface to surface contact, choose a manual. The source will refer to the softer or the flexible component. For this example, the source will be referring to the pipe, because the pipe is flexible and is softer than the roller. So from here, we'll choose the source, put a name, the pipe. So the pipe, and we'll choose from the selection options, we'll choose feature, angle, element, phase. By one click, all the elements should be selected together. If not, probably you can change the setting of these options. For example, here you can change the tolerance to smaller or larger. So by defining a larger tolerance, your selection will be much easier to select larger piece of information. With smaller tolerance, that means you might need to consider the angle between these. For example, this might be just a 5 angle difference. So if you specify 1, then you can only choose this row of elements, because all this row of elements is having a 0 angle difference. So we can choose this row of elements only. So for this case, we will just keep it as default, the 38 degree. And this selection is okay, and is what we want. We want to select all the surface of the pipe. And for this one, we'll choose flexible, because this is the deformed component. Click OK. So take note that this surface is top, and we're going to define a target region. For example, click here once to select this roller. Maybe I can rename it as roller A. And take note this surface is top, and we choose rigid, because this surface does not deform, and the master grid point is at the center, because this center will drive the entire roller. So click OK once, and make sure to enter static friction to allow the friction to drag the friction to drag this pipe along. 0.5 probably. I'm using the same value as the example, and probably we can just keep the default setting for advanced nonlinear parameters, so nothing to define at here. We'll proceed to apply. From here, we can look at the arrows. These are the top surface, and these are the top surface. That means the definition is correct. So we are trying to define the contact between the top side of both surfaces. Okay, so this is okay. We will just hide it for now and proceed to define the rest. By using the same region, I can say the pipe, and the target, choose roller B. So this is roller B. Click this roller is rigid with a master grid point at the center. Click OK, and the coefficient of friction 0.5. Click apply. So temporarily hide it and proceed to define the third one. So between the pipes and also roller C, choosing the surface, one of the elements to choose all, and the type is rigid, choosing the center as the grid master point. Click OK, and applying 0.5 to the static friction, and click OK. So now you may try to solve right-clicking and solving. So the solution will take, in my previous solve, once you click the solve button, you will need to wait. So for how long? So in my previous solve, it took about 2 hours. So this is 1 hour 58 minutes. So it takes this long duration just to solve this simulation. So let me just quickly show you the animation results. So from here, double click on structural. So these are the increments result sets. We can quickly look at the nonlinear stress results and animate across iterations from iteration number 1 to the final iteration, and we can click play. So this is how it looks. So with this, I end my tutorial on row forming. So I hope you enjoy it. Thank you.